With seismic activity on the rise, the Richter scale, which we use to measure the intensity of an earthquake, has been in the news and therefore part of more group discussions. The math behind the Richter scale is what we will be discussing today. Hi, my name is Tom Atwater, and we're going to be investigating the solving of exponential and logarithmic equations. We're going to start by examining the relationship between exponents and logarithms. One-to-one properties. For any exponential function, f of x is equal to b raised to the x. If b to the u equals b to the v, then u is equal to v. For any logarithmic function, f of x equals log base b of x. If the log base b of u is equal to the log base b of v, then u will be equal to v. We can try this out by looking at an example and solving this particular equation exactly, algebraically, for the value of x. And the way to do it is, we look at the equation itself and say, okay, if we can write each side as an exponential expression, that is, if we can have a base raised to an exponent, the same base raised to the exponent, then we can say that the exponents are equal. So let's take a look. The first thing I'll do is divide both sides by 36. And what that will give me is 1/3 raised to the x over 5 equals 4 divided by 36. But of course, 4 divided by 36 is 1/9. And 1/9, lo and behold, is 1/3 squared. Therefore, we can say now that we have 1/3 raised to an exponent, and we have 1/3 raised to the exponent. Since those two exponential expressions are equal, it means that those powers have to be equal. That is, x over 5 is equal to 2. And therefore, x is equal to 10. So, there we have a good way of using those one-to-one properties. Let's look at one that may be easier to solve graphically than it is to solve algebraically. Solve graphically and support your answer algebraically the equation e to the x plus e to the negative x, all divided by 2, is equal to 4. So as I said, let's first do this graphically. So you enter that into your grapher, and here's the graph. Notice that the original equation that I had, the left-hand side, the e to the x plus e to the negative x divided by 2, that's an even function. And remember, with even functions, we expect symmetry, which we see now in this parabola-shaped graph, which means we will have the first solution the grapher gave to us right here of x equaling approximately -2 and 6/100ths. And that's rounding it off. But we know that we're going to have another answer over here, so let's take a look at what the grapher gives us for that. And our solution, of course, it's the positive of that. In other words, 2 and 6/100ths. And that's, of course, what we expected from that. All right, what about solving this algebraically? Let's take a look at what that would mean. What I'm going to do is multiply both sides of this equation by 2 times e to the x. And the reason I want to do this is it's going to clear the denominators, but it's also going to allow me to reformulate this as a quadratic equation. So let's take a look. I have to distribute the 2 times e to the x on this side. Of course, we know that the 2 will cancel the 2 out to 1, and I'll have e to the 2x. Because again, when you multiply exponents, you actually add the powers. Then I'm going to have plus e, adding the powers, x plus a negative x, e to the 0. And on the right-hand side, I will have 8e to the x. Let me subtract 8e to the x from both sides, that would give me e to the 2x minus 8e to the x plus, and e to the 0, of course, is 1. And now what I want you to notice is that this is a quadratic equation. It's obviously in a form that may not be obvious at first. However, this is e to the x squared minus 8e to the x, where I can treat each of those as if they're my variables. In other words, e to the x is my variable. So I have my variable squared minus 8 times my variable plus 1 equals 0. So it is a quadratic equation. In this particular case, it doesn't factor, so you'd have to use the quadratic formula to get that answer. But we already know what that's going to do for us. It's going to give us the answers that we got from the grapher, which is to say, if we were to plug them in, we would get x equals plus or minus 2 and 6/100ths. And that's approximately, because again, we rounded those off. All right. Now, when a logarithmic equation is used, was solved algebraically, it's important to keep track of the domain of each of the expressions in the equation that's being solved. A particular algebraic method may either introduce an extraneous solution, or even worse, it could lose a valid solution. So let's take a look at an example that will show us this in action. We have solve log of x squared is equal to 6. Let me show you two different methods of solving this. The first one, remember, this is the common log, so the base is 10. So this really says x squared is equal to 10 raised to the power of 6. And if I continue through this, that is, take the square root of each side, we'll get x is equal to plus or minus the square root of 10 to the 6th. Now, the square root of 10 to the 6th is 10 cubed, right? So this tells me that my answers for x are plus or minus 1,000. So there are two answers that work. Now, you may say, well, wait a minute, you can't take the log of a negative number. And you're absolutely right, but remember that we're squaring x, and therefore, when we take the negative 1,000 and square it, it becomes positive, so it's okay. I said I was going to show you another method for solving this, so let me do that now. Remember the power rule that says we can take the power and bring it down in front of the exponential of the logarithmic expression. So we get 2 log x equals 6, which means log x equals 6 divided by 2, which is 3. Now we use the definition to say that x would equal 10 cubed, x would equal, 1,000. Well, okay, that's great. It gives us the answer, x equals 1,000. However, we found by this particular method that there are two solutions. So that's where we need to be careful when we're using these methods of solving, that we check to make sure that we haven't either, in this case, lost a root, or we haven't actually created what's called an extraneous root. When we compare two numbers using what is called the order of magnitude, we are mathematically comparing the common logarithm of the two numbers as a difference. For example, when we say that a dollar is 2 orders of magnitude greater than a penny, we are saying that the log of $1 is 2 and the log of 1 penny is 0, so the difference is 2 minus 0, or 2. Now, you may have seen this concept used in the pH scale, which measures acidity, as well as in the Richter scale, which measures earthquake intensity. Let's look at the formula for the Richter scale. The Richter scale, magnitude capital R of an earthquake is given by capital R equals the log of A divided by T plus B, where A is the amplitude in micrometers of the vertical ground motion at the receiving station. T is the period of the associated seismic wave in seconds. And B accounts for the weakening of the seismic wave with increasing distance from the epicenter of the earthquake. Let's work an example of where we use the Richter scale formula. Let's look at how many times more severe was the 1978 Mexico City earthquake, which had an R value of 7 9/10, than the 1994 Los Angeles earthquake, which had an R value of 6 6/10. So let me get to a screen where we have plenty of room to work this. Remembering that Mexico City was 7 9/10 and Los Angeles was 6 6/10. What we want when we want to compare orders of magnitude, we want to take and subtract the R1 minus R2. And we know that that's going to be 7.9 minus 6.6, but we have to look at it in terms of the Richter scale, which tells us that it's the log of the amplitude A1 over T plus B. And from that, we would subtract the formula for R2. So minus log A2 over T plus B. And let's simplify the right-hand side. At the same time, I'll plug in the numbers for R1 and R2. On the right-hand side, we're going to be subtracting the log of A sub 2 over T, and we're going to be subtracting B, which means the B's will add up to 0. The B's will add up to 0. However, we'll still have then the log of A sub 1 over T minus the log of A sub 2 over T. And now using the rule that the log of m minus the log of n is the log of m divided by n, we will have the following. 7.9 minus 6.6 is 1.3. But now, since we're going to divide those, the t's are going to cancel each other out, and we'd be left with the log of A sub 1 divided by the log of A sub 2. So now what we can do is apply the definition of the logarithm and say, therefore, A sub 1 divided by A sub 2 is going to equal the power, the base 10, right? Because common log is base 10, 10 raised to the 1.3. And 10 raised to the 1.3 is approximately 20. It's 19 and a little bit, which means then that the Mexico City earthquake was about 20 times as severe as the Los Angeles earthquake. Now let's turn our attention to pH, because I mentioned that earlier. In chemistry, the acidity of a water-based solution is measured by the concentration of hydrogen ions that are in the solution in moles per liter. The hydrogen ion concentration is written as H with a raised plus sign, like it looks like H raised to the power of plus. Because such concentrations usually involve negative powers of 10, we use negative orders of magnitude to compare the acidity levels, because the double negative, of course, would give us a positive. So let's take a look. The measure of acidity, which is pH, is the opposite of the common logarithm of the hydrogen ion concentration. In other words, pH is negative the log of the hydrogen ion concentration. The more acidic solutions have higher hydrogen ion concentrations, and therefore they have lower pH values. Let's see this in action by looking at an example. The pH of carbonated water is 3 9/10, and the pH of household ammonia is 11.9. Part A, what are their hydrogen ion concentrations? Part B, how many times greater is the hydrogen ion concentration of carbonated water than that of ammonia? And part C, by how many orders of magnitude do the concentrations differ? So let's start off with part A, in which we want to calculate the hydrogen ion concentrations. Water, remember, we were given the value of 3 9/10, and ammonia of 11 9/10. And therefore, we would set up the following, using that formula that we were given, we would set up the following, that negative the log of the hydrogen ion concentration, H plus like that, is going to be equal to 3.9. And of course, I would want to put the negative on the other side. So let me do that. Changes that to a plus sign, because now what I can do is use the definition of logarithm to say that the hydrogen ion concentration would be equal to the power 10, the base 10 raised to the negative 3 9/10. And when I plug that into the calculator, it'll give me an answer of 1.26 times 10 raised to the negative 4. Okay? So that's our carbonated water. We need to do the same thing for ammonia. So for ammonia, we have negative the log of the hydrogen ion concentration, and that's going to equal 11.9. But again, I will put the negative on the 11.9. That makes that positive. We apply the definition, and we get the hydrogen ion concentration is 10 raised to the negative 11.9. And when we plug that into the calculator, we'll get 1.26 times 10 raised to the negative 12 power. So those are our hydrogen ion concentrations, as in moles per liter. That's the units of measurement. Alrighty, part B. Part B, what we want to do is take their ratios. So I'm going to take the ratio of these two numbers. And what I will actually do, because it's a little bit easier, is I'm going to use the powers, that is 10 to the negative 3.9 and right here, and 10 to the negative 11.9. Now, why am I going to do that? Because even though I'm going to get the same answer, it's a little bit easier to see using these powers. Because if I do that ratio, in fact, let me leave all that up, but erase a little bit, just enough to give me the room to show you that ratio. That ratio is going to be 10 raised to the negative 3.9 over 10 raised to the negative 11.9. Well, now you should recognize this. When we're dividing two exponential expressions, all we need to do is subtract the powers. In other words, negative 3.9 minus a negative 11.9. Well, the double minus is positive, so it's negative 3.9 plus 11.9. And so that answer is 8. So we get 10 raised to the power of 8. And that's the ratio of the carbonated water to the ammonia. So the last part of this is to talk about what is the hydrogen ion concentration, orders of magnitude, compared to the ammonia. And the answer is it's 8 orders of magnitude greater than that of ammonia. Now, interestingly enough, let's go back to their pHs. Their pHs are 3 9/10 and 11 9/10. And if we subtract their pHs, what do we get? 8. And really, that shouldn't be a surprise, because that was the whole point of the exercise, was to show that the pH is already a scale that uses orders of magnitude. We were going through the mathematics behind it, to explain how that order of magnitude works on the pH scale. Let's look at a different type of application now, one that uses exponents in its formula. And it's called Newton's law of cooling. An object that has been heated will cool to the temperature of the medium in which it is placed, such as the surrounding air or water. The temperature T of the object at time little t can be modeled by capital T of little t is equal to capital T sub m plus parentheses T sub naught minus T sub n times e raised to the minus kt for an appropriate value of k, where T sub m is the temperature of the surrounding medium and T sub naught is the initial temperature of the object. Let's look at this particular one by doing an example where we have a hard-boiled egg, which is measured with a temperature of 96 degrees Celsius, and it's placed in water that's 16 degrees Celsius to cool. 4 minutes later, the temperature of the egg is 45 degrees Celsius. Use Newton's law of cooling to determine when the egg will have a temperature of 20 degrees Celsius. Of course, whenever we read a problem like that, it's important to pick out the information that's going to be necessary to solve it. And so, very quickly, 96 as the temperature of the egg. The medium, the surrounding medium, is 16 degrees. It takes 4 minutes to cool to 45 degrees, and we want to know how long will it take to cool down to 20 degrees. So what I did was I extracted that information and I wrote it down so that it would be available to us. Here's the formula that we need to plug all of this in. Now, this is a two-part problem because the first thing we're going to do is solve for k. And we do that because we were given some initial information that allows us to plug all the variables in. We're given a number for each one except for the k. So let's do that. We know that the temperature that we're interested in it's coming down to is the 45 degrees. The temperature of the medium is 16 degrees. The initial temperature of the egg, 96 degrees. The temperature of the water, again, is 16. That's going to be e raised to the 4k because, of course, the time was or is 4 minutes. So this is 80. We're going to subtract 16 from each side, which will give me 29. That means this will disappear, and therefore you should see that I can divide both sides by 80, and I will then have the following result. My 4k. And now I need to get k out of the exponent. And remember, the way to do that is to take the logarithm of both sides. So the natural log of 29 divided by 80 is going to equal negative 4k. And then all I need to do is divide both sides by negative 4, and that'll give me my k value. And when you plug that all into the calculator, work it all out, we find out that k is equal to 0.2537. Okay, so that's the k value that I now need to plug in to the original formula right here. And that will then allow us to continue the process and find how much time it's going to take to cool down to 20 degrees. So let me do that. What we now know is we're interested in it cooling down to 20 degrees, right? The initial, or the temperature of the medium is 16. The initial temperature we said was 96. The temperature of the water we said was 16. and that's going to be e raised to the negative 0.2537 t. It's a very similar problem. It's just this time we're solving for t, but the process will be the same. And that is, I want to subtract 16 from both sides, which changes this to a 4. Then this still, of course, is 80, so I would divide both sides by 80. Now, 4 divided by 80 reduces to 1/20th. So I would have 1 over 20 equals e raised to the negative 0.2537 t. I take the log of both sides. Natural log of 1/20th equals negative 0.2537 t. I divide both sides by the negative 0.2537, which gives me a t value, which is equal to 11.81 minutes. So that's how long it would take to cool down to 20 degrees Celsius, 11 and 81/100ths of a minute. Well, now it's time for you to try a problem just like this. So let me give it to you. A cup of coffee has cooled from 92 degrees Celsius to 50 degrees Celsius after 12 minutes in a room that's at 22 degrees Celsius. How long will a cup of coffee take to cool to 30 degrees Celsius? Pause the video while you work on this problem. When you are finished, restart the video to check your solution. Let's find out how you did on this problem. I've already extracted the important information and written it down here. There's our formula. It's a two-part problem. First, you have to solve for k, then plug k back in and solve for t. So let's get started. We know that the temperature that it comes down to is 50 degrees. The temperature of the surrounding medium is 22, plus the initial temperature, 92. Minus the 22, and then it's e raised to the negative 12k. So once again, subtract 22 from both sides, right? And this becomes over here 28. 92 minus 22 is 70. So we will divide both sides by 70, and what I have is 28 divided by 70 equals e to the negative 12k. I need to take the natural log of both sides. That would give me the natural log of 28 over 70 equals negative 12k. I divide both sides by negative 12, and I find that my k value is equal to 0.076636. That's my k value that I now plug back in here, and I can then solve for t to find out how long it takes to get down to 30 degrees. All right, so let me clear off that board and rewrite the problem for the second part of it. And the second part, again, is we want it down to 30 degrees, and that's going to start off with 22 as the medium, plus the 92 minus the 22, and then it's e raised to the negative 0.07636 t. All righty. So now, same process. Subtract 22 from both sides. We have 8 over here. 92 minus 72 still remains at 70. Divide both sides by 70, and we can reduce that fraction a little bit. It becomes 4/35. So 4 over 35 equals e raised to the negative 0.07636 0.7636t. Now, I take the natural log of both sides, and I get log 4/35 equals negative 0.07636t, and then divide both sides by the negative 0.07636, and we come up with t equals 28.41 minutes. So 28 and 41/100 minutes is how long it would take the cup of coffee to cool down to 30 degrees. I hope that's the answer you got when you worked the problem out for yourself. So we're going to finish today's lesson by examining what's called logarithmic re-expressions. And first we'll start off with a linear regression. You know, the linear regression is something you're very familiar with. Y equals a times x plus b, or y equals mx plus b. And that's a very familiar regression that we've run often. What we're going to do now is look at how can we use that regression with both natural logarithms as well as exponentials and powers. And this is the way we do it. The regression for the natural log is y equals a constant, plus b times log of x. So as you can see, we've replaced the value of x, the variable x, with log of x. For the exponential regression, we have y equals a times b raised to the x. That's an exponential regression because the variable x is in the exponent. The power regression, although it looks similar, you'll see is y equals a times x to the b. The difference being that the variable is in the base of the exponent this time. So, of course, I think the best thing to do would be to look at graphs that explain this, because a picture is often easier to see what's going on. So, for the natural logarithmic regression, remember that the natural log has a curve like this when you graph it. And what happens is this: you take the x value and you re-express it as the log of x, and what happens is it converts to a linear regression. And obviously you can see that in the diagram, that it's gone from the curve to the straight line. Well, let's do the same thing for the exponential regression. In the exponent, you should recognize the shape of this curve, right? It starts off slow and then has a very steep slope as we continue to go. In this case, we re-express the y value right here. Y value is re-expressed using the natural logarithm, and what happens is it converts it to a linear regression model. Finally, if we look at the power regression, what happens here? Again, this is a power curve, and what happens this time is we convert both x and y and re-express them using logarithms, both of them this time. And in that case, we convert it to a linear regression model. Now, what's interesting about this that you should know about is when your calculator is actually doing these regressions, this is the method that it uses. So it's the same method built into the calculator automatically, so it's working behind the scenes. Therefore, you're being familiar with the shapes of the curves. That is to say, with the logarithmic curve, with the power curve, or the exponential, will make choosing the correct regression a lot easier. And of course, one of the methods you can use is sort of a guess and fiddle method, where if you think you have the right regression, run it. If it's a straight line, then you'll know that you've picked the correct regression. Great work in today's lesson. So in this section, we explored exponential and logarithmic equations and how to solve those in terms of applications to real-world problems. So be sure to work the exercises that your teacher assigns, and we'll see you next time.